on my jaw for a minute while this warms up, and I just make sure that my string's working here. Yeah, looks like we're good. So I have my SVT-3 PRO. This is the one that I put new transistors in a few months ago. Basically what I have in my hand is the notes page from the last time that I started this up with the new transistors in there. The last time I did this check, I was 10, 11, 11, 10, 5, you know, basically within 1.25 millivolts across all the transistors. So that you can see what we're working with here. This transistor bay right here, the cooling plate with the fan blowing through here, not really the most ideal of arrangements, but that's fine. What you're supposed to do to check bias in this amplifier is measure the voltage drop across all of these 0.47, I think they're 0.47 ohm resistors, and if you were gifted with brain calculation skills, you'd be able to figure out how much current was going through here, but they just published a spec that it's supposed to be less than 25 millivolts at idle, and there is a variance allowance of plus or minus, it's like 100%, 125%, I don't remember exactly. My old ones were really bad. There will be another video on the channel about that shortly, but in the meantime, what we've got here, so I have my multimeter out, and I'm just going to check these one by one, and we'll see how close to the last readings I took were. Volts DC, having an unexpected result. Oh, yeah, millivolts DC, how about that? Always remember, auto ranging only gets you so far. There we go. So this one's at 20 right now. So there's been quite a bit of settling in the trim pot, I guess. It has drifted upward over time. I'm going to let that settle on the meter. Waiting. I don't know if that's actually visible. Alright, well, this thinks about what it's done for a sec. I'm going to set up a new page for this. I didn't, unfortunately, put the kilowatt in there. I wasn't planning on making any adjustments to the resistor, to the pot, so that's fine. You know what day of the week it is, 2:20. Actually, I'm not even sure I know where my kilowatt is. Well, anyway. Alright, so I typically start at the back. It doesn't really matter as long as you're consistent with yourself. You are supposed to do this measurement no load. 19.3. Just gonna call it 19.30. Now these should all be different. I'm gonna let this just sit and think about itself for a second. I wonder if in the meantime I can find the kilowatt. One being meter thin because it's too big for that. Well, just as a sanity check here. Yeah. Okay. And we have been on the DC range. That's good. Oh boy, this is obnoxious. My inclination is to stop this, let this thing sit for 20 minutes, and then come back and see what's what. I mean, it's definitely at operating temperature. let's do this. Let's just take a quick reading and not wait for it to settle and see how far apart they are. Alright, so first 19.15 was where it started. Second, 20.24. $19.13. $18.14. $19.82. Good year. $20.44. $19.32. $19.11. Okay, so with the understanding that this information is going to be sideways for one of us, I might as well make it you, or me rather, that has it sideways. So if we look at my last round of readings, okay, so if we look at my last round of readings, you can see that the original I don't know, I have two sections here. One is labeled lobeless recheck, so let's go with that. I got them to 15.9, 16.6, 15.9, 15.7, 16.2, 16.6, 16.2, 16.1. So these two are the hot ones. They're going to be drawing the most current, no matter what idle current I set. So if we come back around to today, that still is the case. So we've got the 22.4 and 24.4. The two lowest ones are going to be resistors 1 and 8. 19.15, 19.11. That's not the case that they're both the lowest anymore. This 18.14 right here is lower. So the question is, why would it have changed? The answer, I don't know. But the fact that it's still within tolerance is good. What I'd like to do is bring this down a little bit. Bring the bias down. In order to do that, I'm going to need the kilowatt. So sit tight. I will be back in however long it takes me to find that. Remember, keep your electrical test equipment with your electric. Oh, there it is. That was easy. All right. So we're going to turn this off. Unfortunately, there's not going to be any way for me to show the kilowatt on camera. So right now we're running at a wall voltage of 120.8. Turn this back on. Voltage dropped to 120.4. Idle wall draw is 0.92, 0.91, 0.92 amps. Make sure the protection relay clicks on. Okay, so we're at 0.95 with everything on. And 120.4, 120.3, so let's do power factor. Yes, it does. Power factor on this bad boy is a whopping 0.62, so sorry about that, everybody. So it's drawing 71 watts, 115 VA. So I guess this is not particularly efficient. Alright, I need my electrical screwdriver. Okay, so we have an advantage in going downward. And we don't have to worry too much about, I need my leads box too. We don't have to worry too much about safety unless we really goof it up and go too far and have to turn it back up again, which happens. Anybody who says it doesn't happen is lying. So what I'm going to do to enable me to have three hands to do this, slip a clip on. And we want to watch the high voltage, the hot pair. Yeah, these are tough to negotiate. See if I can get this out of here so it's a little bit easier to deal with. Okay, that's good. Where did I lose my screwdriver to? Most fun part about working on stuff is always, alright, I'll remove this. A little bit of a squishy boy on that. Just crimping the clamp down a little bit so it holds the probe a little better. And we gotta find the screwdriver again. Cat's here. There's the screwdriver. Okay, let me make this. Should be able to see everything if I do that size. Okay, screwdriver ready to go. Remember, don't put stuff inside your amplifier to hold it. That's bad. Great. Make sure we're getting reading. Great. And then it's this little trim pot right here. And you can see how sensitive it is. All right. I basically moved it far enough for it to go break free, and it dropped by 50%. Our wall idle now, by the way, it's fallen to 0.88 amps. So I'm going to let that settle for a sec. I goofed up my clamp here. Doesn't open or close in a straight line anymore. That's good. Neither does the other one. Well, nobody's perfect. So we'll get this back in here where it goes. While I do that, there we go. I'm gonna have to order new ones at some point. All right. This used to be live updating. What happened? It's just gonna smash cut there. What all these buttons do. Full screen. There, it's live resizing. Okay. We got the bird update. Sharp-shinned hawk, raven, redhead, canvasback, northern shoveler, 2, ruddy ducks. Some good and bad Canada geese, 7 and 2 apparently. I guess the 2 were the ones probably making the noise. Let's find out. And cormorants. We have cormorants at this lake, and they check in with one another apparently. Alright, so we've stabilized, hopefully, still at 0.88. Just make sure the voltage is still at 124. .64 watts. So you can see these transistors take quite a bit of load to run, or current to run at idle. 105 VA. Let's get our readings one last time, and then we'll call it good. I've got one more live stream testing thing to do today, and that's to try this with a mixer again. 13.53. .44. 13.67. 12.96. I'll call it 12.97. Okay. 13.92. 14.41. I love the multimeter flipping out every time I wiggle the cables. 13.52. That's shoot, Faraday's law in action. 13.44. So yeah, pretty happy with how stable this has been. Replacing the transistors seems to have helped a lot with the cutting out and scratchiness. I seem to be getting more output volume, more current available when I go through the speaker jacks than I did with the banana plugs. I wish this thing had to speak on, but it's the old version, so that's life. Basically, through regular use, these caps have all tested fine. These caps over here have tested fine. There's really nothing on this board other than that needs to be replaced. Now, the people at my local amp shop who failed to diagnose this thing correctly, I didn't even have the, must have bumped this, or oh, we lost live updates again. Oh yeah, you're falling, bud. My mic stand's not the best. Okay, so the people that did this diagnosis for me the first time really missed the mark here. They said they did a solder reflow. Oh, my idle draws down to 0.86. Weird. They said they did a solder reflow to solve the signal dropping out, which makes sense if it's a problem with either the input or the output jacks. Now, I had a situation with this amplifier where if I touched, I can't remember which pot it was, either gain or tube gain, one or the other of those, and my signal would go real bad and get very scratchy. So I actually, in a previous video, did a repotting of this, and that did help with an issue. I guess the real problem with this amplifier is that a lot of the stuff that happens to it sounds the same. It creates the same problems. So the one thing that I will say is it doesn't seem to have been any of the tubes except for the time when I got real bad. This is after I had learned to start doing bias on it. I started getting real bad distortion, and I think it was this tube had failed. So, you know, it happens. But, you know, the crossover distortion, the signal cutting out, could have been the protection relay. It could have been the actual device giving up because it was overheating. I don't know. The fan, I believe, bases its calculations off of this could be a temperature sensor. There are also two diode packages. No, these aren't diodes. I don't know what they are. There are two packages on the outside here as well, but it's probably heatsink block. If one device is overheating and failing, and it's not next, whatever it is most likely in the airflow or attached to this, the heater block, or to whatever the one temperature sensor is that changes the fan speed, then it's never going to spin up, spin down, whatever. It's not going to change its speed. Neither everything will run too hot or too cold. And relative to the one that was hot, in this case, the one... let me try that again. Everything can be running normally, and you'll have one that's running too hot. Or if you have the hot one is right next to the temperature sensor, then you'll have everything running cold. So I think in this case what was happening is, looking back at the original data that I had taken an eternity ago, still somewhere in this notebook. So this is me taking a recap. Recap of observations. Let's recap for the 317. Here we go. Here's the original. So the original readings that I was getting with crossover distortion. A little easier to see. So 0.9, which is basically off. 3.8, 8.7, 0.8, 1.4, 5.4, 5.2, 2.3. Average across both sides was fine, but when the average includes a 0, that's when you get crossover distortion at low values. So going a little further, I did my adjustments, and you can see how bad the original matching had become. And I say become, it was probably, there are variances in the manufacturing tolerances that come from International Rectifier, and apparently they were within whatever 0.2 millivolt or something. I don't remember reading. There's a lot of good information on TalkBase about this. But I'm putting it in a place that's not TalkBase because I'm an outsider. I don't speak the language. Anyway, the original design called for a looser spec than what International Rectifier was shipping. So that said, they weren't matching them very closely at the factory, if at all. And you end up with a situation, most likely, where you have one that's taking a bit of a higher load than its friends, and you get this situation where I have my cold at 1.4, which is still pretty much just off at idle, and my hot was up about 30, which is over spec. You're not supposed to have any that are over 25. If you do have this situation, it's 100%, 125%, something like that. I might have that. It might be like a 50% overage. I don't know. But it's supposed to be within some limit of the rest of the average. And when we've got 12.4, this is more than twice that. So just to give a quick rundown of the percentages. Scrolling back. Hi. Okay. So the old transistor set, I took a set of readings that were at 9.3875 and 9.8625, which are fine for averages. We had some settlement in the way that they were running. We had 3.23. Hi, I'm being assaulted by a cat. Hi, bud. .23, 10.66, 21.03, 2.63. So we have two that are not very far into the conducting. I forget what this actually is establishing, but they're not very far into the bias range. On that side, and then on the other side, 459, 1405, 1435, and 646. So again, two that are not very far into the conductance range. Hi, thank you. And So percentage-wise, the variances are 65 minus 65.59%, the below average, plus 13, plus 124, minus 71, then minus 53, plus 42, plus 45, plus 34, or I'm sorry, minus 34. So that's not ideal. When you look at the original Power It Up, admittedly with a load attached, but we had the averages of 5.74 and 5.76. The variances were minus 4.2%, 3%, 2%, 2.5%, minus 1.7, then 0 right on average, 295, minus 174, minus 122. So everything was within 3.5% at that point. So yeah, there's something to be said for bringing your pieces into the modern age. So that's going to do it for this exploration. We'll let you know that the 7 good Canada geese were not making noise and regarded my friend as a stupid deer. There was also a pileated woodpecker, so there you go. Alright, here's the cat. Hi, Hercules. You're always helping. Thanks for watching, and back more with some analysis later.